In this video, we'll be going over the canonical form of the bivector in the spacetime algebra. So first, let's consider the recall the square. So square of a bivector. So you have a square. F squared is just equal to um, the magnitude of f squared, and then e to the 2 phi I, where this right here comes from the phase, and then that's equal to that can be expanded like this as well, e plus bi, then this squared, which will just give e squared minus b squared plus 2 e dot b I. And in terms of the physical significance of these quantities, this right here is known as the electromagnetic Lagrangian density. Lagrangian density. So this is what's used to construct a Lagrangian in electromagnetism, which makes sense because if you were in traditional electromagnetism, you typically write out the Lagrangian as negative alpha beta f alpha beta, like this. This is traditionally how the Lagrangian density would be written in tensor mechanics. But in this, you just have, a bivector, so you just square it. So it's overall a much simpler mathematical formalism than in tensor mechanics. And then this right here, the paper refers to it being related to axions. So they say it's related to axion contributions. Now, I don't exactly know much about axions, so all I know is that they're a hypothetical particle that haven't been proven to exist experimentally. So, like physically, this to me it makes sense for this to be an unphysical term, or for more precisely for this to be zero when you're dealing with pure electromagnetism, which is what ends up being the case, as we'll see. So, before we continue, we're gonna simplify some stuff, some notation. So we're gonna denote. E squared minus b squared, which is equivalent to the projection of f squared onto its scalar components. So we're going to denote that A, and we're going to write this part to EB. That is the projection of f squared onto its pseudoscalar part, but then the inverse of that. So that is equal to B. And because of the form we did before, let me see if I can find it real quick. Yes, right here, where you can represent phi in terms of these values. Well, now we'll just have B over A. So let's go back down. So we can say, therefore, you can represent phi in terms of, what is it, 1/2, yeah, 1/2 tangent inverse of B over A. All right, this is a result that we've already seen before, but we're just calling things B and A just to simplify some of the notation. the canonical bivector, or I'll just say the canonical form, is therefore f equal to negative phi I and big F. And this is because of the fact that F is equal to E phi I and then little f. So the canonical form can be found and calculated if you know the angle and you know original f. And this implies that f here is equal to cosine of phi e plus sine phi e and plus cosine phi b minus sine phi e times the pseudoscalar. And this just happens when you expand out. So like the reason why this equality holds here is because of cosine phi plus I sine phi times e plus b I. If you expand this out, FOIL it, then you get this result right here. Or actually, what I'll do is I'll move this up here, change its color. Like that. Now what we're going to do is look at some of the, how we can rewrite a few things. The paper, as I've seen it, doesn't exactly give a good reason why you would want to rewrite stuff like this. So I'm not going to present the reasons why things can be rewritten. I'm just going to present them as look, you can do this. So I'll just write this as look, you can do this. So the first thing is that they make this claim right here that 2 cosine squared phi is equal to 1 plus a over the square root of a squared plus b squared, which this implies that through some trigonometric identities, this implies that this fraction here is equal to cosine 2 phi. And the specific trig identity here that gives rise to this is 2 cosine squared phi minus 1 equals cosine phi, or sorry, cosine 2 phi. So you have that. I don't like how I'm not writing, kind of like in going down and up. So you can do that, and also you can have, or you can see that this would imply, like if you have cosine squared of 2 phi plus sine squared of 2 phi. That's always equal to 1. But we know what this value is. You know what this value is, so we can say that sine squared, or sine 2 phi, is equal to 1, the square root of 1 minus cosine squared 2 phi, which is just equal to the square root of 1 over the square of this. So 1 minus the square, so you'd have a squared over a squared plus b squared. And if you simplify this fraction, you end up with the square root of a squared plus b squared minus a squared over a squared plus b squared, which ends up just being equal to b over the square root of a squared plus b squared. So because of this assumption right up here, it turns out that you can rewrite cosine 2 theta, or 2 phi, in terms of a over this magnitude, and then sine of 2 phi over as b over this magnitude. And this becomes useful if you consider, so this becomes useful if one considers the complex conjugate of f, which should be e to the negative phi I, this canonical form, but you can replace the canonical form here, this f, little f, because it's equal to this up here. So it's equal to e to the 2 phi I negative f, and we know f, and so it ends up being a similar expansion to this, except where instead of cosine phi and I sine phi, you just have these a over and then b over magnitudes. So you end up with an 1 over the square root of a squared plus b squared. Then you have a squared, sorry, not a squared, you have ae plus b, capital B, plus a 1 over square root of a squared plus b squared. And then you have ab minus b e I. So this just gives a way to compute. This gives a way to compute the bivector f, its complex conjugate, utilizing its original, because a and b, if you recall, come from the original f. They're the scalar values. Now, then using this, you can consider different options. So if you have a as being equal to 0, then this is equivalent to saying that e squared minus b squared is equal to 0. Otherwise said, the Lagrangian density vanishes. So then this would imply that your cosine of phi, which comes from up here, so your cosine of phi, so because of the cosine phi equal to the square root of 1 over 2 plus, so it would be 1 plus a over square root of a squared plus b squared, implies that this gives cosine, or actually, wait, hang on. it should be this. Yeah, it should be that. Implies that cosine of phi, if a is equal to 0 here, then this is 0. So then you just have cosine phi equal to 1 over the square, or 1 over 2, which only happens when pi is equal to, or phi is equal to pi over 4. And what this does, if we then take this pi, or this phi equals pi over 4, and we insert it into the canonical form of the bivector, you're going to get that this is equal to 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2. So you end up with little f equal to 1 over the square root of 2 e plus b plus b minus, or then plus 1 over the square root of 2 b minus e I. So essentially, you end up with this canonical bivector being the dual by basically you have the e plus b and then b minus e, which are components of the traditional bivector field, and then you have components of the dual field in it, and it's a superposition of that. Now, if b is equal to 0, then that implies that the dot product is equal to 0, which means that whatever the axion contribution goes to 0. And that makes sense in electromagnetism, that going to 0, because you don't have axions. And so this implies that sine of phi is equal to 0. And sine of phi equal to 0 implies that phi is equal to 0. So there's no phase. And if you insert phi equals 0 into the decomposition of the canonical bivector here, if you insert phi equals 0, then you get f, the canonical, is just e plus bi.